So welcome to Microservices in Action at the Dutch National Police, and thank you for joining me. It's good to see that the room is fairly full. There are a couple of seats left up front. I won't get off stage, so you're safe. Does anybody know what's on the screen behind me? Which room is this? Yes, that's absolutely correct. We're in room 4. Which room is on the screen behind me? Shout if you know it. 112, yes. This is the emergency room of The Hague. When you call 112, that's where the police and the fire brigade and the ambulance pick up your phone call. And this is one of the rooms that one of the teams where I work at the police is making software for. So I have a bit of a challenge. This is typically a talk that lasts about 60 minutes. I have 40. So I can either talk really fast or leave some stuff out. So every now and then I'll be asking you if you're interested in the next slide. And if not, I'll just skip through it. And then we'll see how far we will go. My name is Bert Schrijver. I am CTO at Open Value, which is a small Java startup that does Java development and consulting. Basically anything that helps clients deliver better software faster. But since the startup life is so hard and rough, I also work at JPoint, which is a Java consultancy firm, also in the center of the Netherlands. I currently am doing a project at the Dutch National Police. I run the NL-JUG, the Dutch Java User Group. So I'm curious, how many of you are developing in Java? Okay, keep your hand up, please. And I'll lower your hand if you're not a member of the NL-JUG yet. All right, let's talk. I am on Twitter. You can find my Twitter handle on most of the slides. I have already published my slide deck on Twitter. So no need to take pictures. You're allowed to take pictures, obviously, but you can also find them on Twitter at @Schrijver. So for the next 40 minutes or so, I'll start with an introduction. I'll talk about methodology and culture. I'll talk about architecture, how we develop our front end. Obviously, we have a backend too. How we develop stuff and how we test stuff. What we do to get stuff running and get it out in production. And I'll end with explaining some of the challenges we had and stuff we'd like to work on in the future. So this is not really a best practices talk. I'm just sharing how we work and what works for us. It might work for you too, it might not. It always depends. So I'm going to share lots and lots of stuff from different angles. I don't have time to really go in depth, but you're free to approach me and ask me afterwards. I'll be here for the whole day. You can also easily reach me on Twitter. So the Dutch Police. Is any of you familiar with the Dutch Police? Okay. So the police does things like, protect the people and maintain the law. So I work at the product line Cloud, Big Data, Internet, which is a small department in Driebergen, in the middle of the country. And over there, 5 teams are building fairly high-tech stuff. We're building everything in a private cloud environment. We use exclusively open source software. And we build applications that support various police-related teams. That's about what I'm going to share about it. We do everything ourselves, so development, maintenance, and support. And what I'm about to tell you is how we work at this product line. It's not necessarily how the entire Dutch Police works. It's how our small team of about 30 people works. I'm going to share anything about the technology we use and how we work. I'm not going to tell anything about the type of applications we build and what they're used for. But obviously you're free to use your imagination. So let's start with methodology and culture a bit. I'm going to speed through this a little because most of this probably will be clear to you already. So we have 5 teams. Every team has its own backlog and there's one product owner that's helping all these teams work on the right things. So what we do is at the start of every sprint, so our sprints are synchronized. At the start of every sprint, we have an overall planning with the agile coaches where we determine the overall priorities and the dependencies between teams. And then the teams go into planning themselves. Our planning ritual is fairly minimal. We do work with story points, but only as a guide to see how much work we can fit into a sprint. So we don't measure anything like velocity because I think that story points are something that are really easy to influence. So what we do when we estimate stories is we estimate how much man days of work will the story be. So that's a number, where we do use the Fibonacci sequence. And then when we start planning a sprint, we count the days that everybody will available for the next sprint. So counting, I don't know, people that are away or some holidays. This adds up to a number. Then we start adding stories in the sprint until we fill up this number. So it's fairly basic, but for us it's working fairly well. We only want to be predictable in terms of how much work can we fit into a sprint. We try to do usability tests while we're developing our stuff, because if one thing is important is that it's actually usable by our users. And we try to minimize the amount of meetings we do. To administer all our tasks and documentation and stuff, we're using Fabricator. So how many of you have heard of Fabricator before? Yeah, almost nobody. Well, Fabricator is actually pretty cool. I once called it an open source clone of the Atlassian suite. And then somebody responded angrily on Twitter that Fabricator had some stuff before the Atlassian suite had it, and this turned out to be one of the Fabricator developers. But it has fairly similar functionality as the Atlassian suite has. So you can administer tasks, there's a wiki, you can do sprint and project planning, you can administer mockups in there, it can connect to your source repository, you can do code reviews. It basically has anything you need, and it's free to use. Facebook used it, Dropbox used it, Pinterest used it. It's been out there for a while. So, well, we try to do a modern way of software development. So, continuous delivery and DevOps is a no-brainer. We try to keep our feedback loop as short as possible. So, whenever we do something, be it commit a piece of code, deploy something into production, we want to have feedback as fast as possible, either automated from a build or a test, or from our end users. So, we try to make it very easy for them to give feedback about the stuff we built. They just need to push a button. They can type the feedback, it lands in our support box. I always say I reserve the right to wake up smarter tomorrow. And kind of extending that, we know that stuff is going to change. So we don't try to plan ahead too much. We know that the world may be different in a week from now. So we build stuff that's easily adaptable, easy to change. We'd rather make a choice now that turns out to be wrong in a week than that we don't make a choice at all or we start thinking too long. So just do the best we can now and be prepared to throw away everything for the next sprint. This is vital for us to be able to maintain speed within the larger police organization. So the police IT is about 1,500 people. And we try to minimize the dependencies we have outside our department. Because if we have a dependency, somebody needs to do something for us, and we can't influence him or her to work faster, then we're kind of stuck. So we try to be able to do everything we need to do to go from idea to working software in production, all by ourselves. We only invest in people by hiring good, smart, driven people that can help our organization progress. We don't buy products. Everything we use is open source. And some of the stuff we're building is open source too. So if you go to github.com/politie, there are some libraries and tools that we've built that we've open sourced. And for all that we do, we try to be very open and transparent and verifiable. So we regularly have people from outside over for a chat on how we're working, what we're doing, and just try to be open and do the right thing. So if we do everything ourselves, how do we handle support? This is a role that cycles throughout the team. So we have 5 teams. In every team, somebody has the role of the support role for the day. So there used to be a different operator and developer role, but now there is more teams. It's just one role per team. And this man or woman has the support phone, does proactive monitoring in our logging systems, and helps end users with their problems. So everybody's on for support, well, at least once every 2 weeks, and typically a bit more often. So let's dive to architecture a bit. Obviously, security and encryption is important for us. We have everything in version control, source code, but also infrastructure, documentation. So we always have a trace of who did what when. We want to be horizontally scalable because theoretically we have 65,000 end users to serve, the entire police organization. No single points of failure. And no runtime dependencies on systems that are not in our control. Because the type of stuff we build, it's most important that this works when there's, I don't know, fire going on around or the internet is broken down. So the stuff we build must always be available for the police organization, even if the rest of the internet is in flames. We standardize on naming, and this seems small, but it's actually a big thing. Because when we standardize on naming, it's easy to automate. It's easy to know where to find stuff. When we know the type of domain that something is, that a service is processing, then we know that the service is called service, well, let's say its domain is, I don't know, geo information. Then the service is called service geo. Then the Git project is called service geo. Then the build is called service geo. Then the dev environment is service geo.dev.something. So this really helps in being able to find stuff and to automate, because in every script we just need one variable, and then we can script it out. We try to choose the right tool for the job, so we're somewhat polyglot. As a result, we now have applications running in production, written in Java, TypeScript, C, Ruby, Groovy, PHP, Scala, JavaScript, Python, Go, Perl, and Kotlin. Are we proud of this? No, not really. It's more followed from the type of application we were building. Most of our backend stuff is built in Java. Frontend is built in TypeScript. We have C for some low-level network stuff. Ruby because of, I think, Puppet scripts. Groovy because of Jenkins pipelines. PHP because of some legacy application we inherited. Scala because of Gatling scripts. JavaScript because of, I don't know. Python because of some operation scripts. Go because somebody wanted to learn Go. Perl because of some operation scripts. And Kotlin because we wanted to explore working with other JVM languages. And, well, Kotlin was the less step than move to Scala right away. So I need to warn you. There's an architecture diagram ahead. And these are typically big with lots of boxes and lines and colors. And if you're lucky, there are icons in there. Well, this architecture diagram is no surprise. So let me take this to you step by step. So this is to give you kind of an idea of how our architecture is set up. So it all starts with the layer we're running on, which is OpenStack, which is an open source cloud management software, and Ceph, which is a distributed storage system. So we're currently growing towards somewhat 500 servers, 1,500 virtual servers, about 24 petabyte storage. I think we're currently about halfway growing there. So if we start all the way at the right, we have some data sources where we pull in data from. So this can be something from the web, or map data, or some other internal sources. We store all the original data we fetch. Because we always want to be able to show which was the original data that we got into the system, to be able to prove that we didn't tamper with the data, for example. And then all this data is fetched by services that we call connectors. So the only role for a connector is to fetch data from a source. And the connector then puts this data on a Kafka topic. So Kafka is kind of a stream processor or a distributed queue. Whenever the message is small, for example, Twitter, we put the entire message on topic. If it's a bit bigger, we put a pointer to the data on Ceph. And then there are streams processors, or we also call them sinks. And these are applications that fetch data from the Kafka topics, process them, and then write them into fast, accessible data stores. So this can be Elasticsearch if we need fast search and indexing, Cassandra if scalability and writing is important, MongoDB if it's document-oriented, and MySQL because we migrated some MySQL system and didn't want to migrate the database. Then there are services which respond to requests from end users, fetch data from a data store, and serve it to the front end. And on the front end, we're running a couple of Angular applications that provide a GUI to the services we provide. So technology-wise, all the green blocks are Spring Boot applications, Angular 5 and 6 front end, and then some data stores, whether it's suitable for the occasion. So for security, we're using a delegated model. So we're currently using Kerberos, but we're moving to an OAuth solution. Whenever a user calls, his front end calls a service, then the service knows which user is calling it. But whenever this service needs to call another service, then it uses the authentication token from the user. So it has a security delegation. And this means that every call to every service is always directly relatable to a user, which makes the security model fairly simple. We don't have system accounts or God accounts. We always know which user we need to serve. So about the platform we're running on, as I said, OpenStack and Ceph. Ceph is also being used at CERN for the Hadron Collider. It's a fairly scalable and fast distributed storage system. And we provide, well, all I can say is general cloud services for the police organization. In addition to that, a couple of thousand managed desktops. And whenever something boots, be it a server, a desktop, or a network component, then we start automating it. So typically by booting over a PXE, over an Ethernet boot. So we kind of playing our own cloud provider, which is fun, but it's also difficult. If you use cloud service from Amazon, then you just flick out your credit card, you push a button, you have a server. We need to worry about storage, about replacing hardware, about managing networks. Of those 30 people, one of the guys is full-time working on networks, on firewalls, on routes, on cabling. And that's fairly different from when you just take cloud service from some cloud provider. So if you have hundreds of servers and 14 disks in a server, it's not really a matter of when stuff is going to break. Sorry, not really a matter of if stuff is going to break. It's going to break nevertheless, but when it's going to break. So a bit of a story about this. So we have a support phone that's being called whenever there's something going on. So we're monitoring our systems continuously. So we monitor the drives to their smart values, and whenever we see that a drive is failing, we automatically create a ticket to the people working in the data center. And then they start working to replace the disk. So it happens that our support phone rings, pick up the phone. Yeah, so you called in the support ticket to replace a disk in this server. And we're right, okay, we have no idea, probably the script did this. Oh yeah, sure. Yeah, I'm currently standing in front of the server, but which disk is it? And we're right, okay, do you have the service tag for the machine? Yes, so we look it up, we log into the machine, take a look at smart values. All right, so it's the second disk. Okay, thanks. And then 2 seconds later, so is the second disk from the top left or the second disk from the bottom right? And then we have no idea if which way the server is mounted. So yeah, I'm pretty sure it's the top left. All right, here we go. Disk goes out, healthy disk disappears. Oh no, that's not the one, put it back, sorry. The broken disk disappears. So is this a problem? No, it isn't, because all our data is stored in at least 3 places in Ceph. So whenever we pull out a disk, only one replica disappears, and then Ceph starts rebalancing to rebalance the data over the entire network storage. So we once lost about 1/3 of the cluster due to some, let's call it power issues, or Ceph needed some rebalancing to do, but in the end we didn't lose any data. So how do we manage all these things? We certainly do not go by SSHing into them and typing shell commands. So we use infrastructure as code. So HashiCorp Terraform to provision machines in the cloud, Puppet to provision and manage servers, and Ansible to provision some of the desktops. So let's take a look at the front ends we're building. So I'd say they're fairly modern. Angular 5, TypeScript, ArcGIS. Well, actually, Angular 6 was released last Friday. So this Monday, one of the teams migrated to Angular 6, so we're a bit behind already. Angular is awesome. For me, being a Java developer is awesome because you have nice ways of componentization. It's fairly structured, and you have TypeScript. How many of you have experience with developing in TypeScript? Okay, oh, fairly a lot. And how many of you have experience developing stuff in JavaScript? Okay, so with JavaScript, it's fairly easy to create an object that represents a cat with a horse's head. So in TypeScript, this is a lot more difficult. But in TypeScript, you have typing. So it's fairly close to typing in Java. You even have stuff like generics. You have interface, you have classes. So for me, it's awesome. It really helps me writing better code. And then there's ArcGIS, which is really useful for managing all the asynchronous stuff, calls to the backend, chaining calls to the backend, stuff like that. So we have Angular for the HTML, TypeScript for the logic, ArcGIS for the asynchronous stuff. What are we missing? One part that Java devs typically aren't good at. Shout if you know it. CSS, obviously, yes. So there's this thing called CSS for Java developers, which is typically called Bootstrap. So we use Bootstrap for our design, responsive design. Currently, we're also investigating Angular Material because it's closer to Angular and it seems to work out fairly nice too. One of the key points in our architecture is that we want whenever something fails in the backend, we want the front end to fail gracefully. So if one service fails, only that part in the front end should fail, and the rest should still be working. And in order to know what's going on the machines of our end users, every error that happens in the console in one of the connected browsers is being sent to a centralized logging system. So we can also see whenever stuff is exploding in the browsers of end users. So every now and then, a feature takes longer than one sprint to release, or we don't want to release to our end users yet, but we don't want to keep it on long-living branches. So how do we manage this? we use feature toggles. How many of you have heard of feature toggles before? Okay, don't need to explain it. So we have a nice serviced microservice backend, and then we started building on our front end, and in the end, we ended up with, I don't know, 40,000 lines of TypeScript in one big repository. So how do we prevent creating a monolithic front end? Well, we didn't, but we found out that we need to work in it too. So currently we're trying to apply microservice principles to our front end too. So by creating reusable front end components that are libraries that can be used by all the applications that we're building. So we have a front end, so obviously we need a back end too. But let's first dive into what does a microservice look like. It's typically small. It does one thing, and it does one thing well. It runs in its own process. You can independently build it and deploy it, upgrade it, scale it. It has its own data store, because otherwise you're just building a couple of distributed things that are connected through one database. You still have dependencies between services. A microservice is typically distributed, otherwise it's not of much use. It can be heterogeneous or polyglot. We see that most of the services we build are built using Java. Some of them are Scala, and we're exploring a bit of Kotlin now. So we have the opportunity to do polyglot, but so far we've mostly used Java. And they better have some form of lightweight communication, because otherwise you have a fair amount of penalty from all the network overhead. So, did we build microservices when we were starting out? No, luckily we didn't. So why did we move to microservices? It was a couple of years ago, two or three. I think the most important reason was scalability. So both in terms of being able to scale out individual parts of our system, but also being able to scale out on development teams, having different teams work on different parts of the same system without getting in each other's way. But also, actually this modularity, so that we could also have independent development of different parts. And if you need to fix some part of the system, then we could only take this part, fix this part, and deploy this part to production. And obviously, microservices were becoming cool then, so this helped. This helped too. We wanted to be some of the cool kids. So how do we do this? Did we do this by just splitting up the system and deploying independent services? Well, I guess you could say yes, but we did some thinking up front. So one of the things that matches well with the idea of microservices is domain-driven design, and especially the term bounded context. So with domain-driven design, you're saying that it's probably impossible to create one unified model for your entire system, because you have different parts of domains that I don't know, something may see a customer different than another part of the system. Domain-driven design says that it's okay to have different models for different parts of the system, as long as you're very clear about the boundaries of those different models and what the interfaces between those different parts of the model are. So this is called a bounded context, and this maps fairly well to microservices, because when a microservice, you can have different domains and different services too, as long as you're very clear about the interface between those services. So we try to divide the current system in somewhat functional models and bounded context. And for every module, we created a microservice. And for every service, we check, does it now only serve one part of the domain? If it did, we're good. If it didn't, we need to split it up anymore. So did we split up everything right away from the start? No, that was simply too much work. So we started with splitting the easy parts off, and then kept the rest in kind of our memory of a monolith. And then whenever we need to change something there, we would take that part out and deploy that as a new service. And actually only a couple of months ago, we threw away the remains of the monolith and took out the last part, which was the part that was handling feedback emails from our end users, I guess, because that had been stable and running in production for a couple of years already. So how does a backend look like? I'd say typical Java backend. Spring Boot, Java 8, Maven. It is stateless, which means that we don't store any state in memory at the applications, so we can easily scale it horizontally. And we run one service in one jar, in one JVM. Well, we used to run them on one host, and then there's then one Git project where it's in. We don't share too many code between services. We used to do this before by sharing, for example, domain models, but it turned out as it wasn't really useful because it created dependencies between services that we didn't want. So we only share stuff that we need in every service. So security, authentication, authorization, logging, and metrics. We need this everywhere. So that's a shared library. For the other stuff, we rather copy code and change it instead of reusing it. We used to make stuff high available through load balancers, and currently we're using service discovery to do this. So I need to warn you, because service discovery is, I would say, an advanced microservices pattern. And if any of you are running microservices and you would ask me, do you need service discovery? Probably not, I would say, because we got away with it for quite some time. So do we need service discovery? Well, you probably know the answer. We think we do, but for reasons. Because we want to have high availability and balanced load without having single points of failure. We want secure end-to-end communication. We're using Kerberos for authentication, and it's fairly picky on DNS verification. So then putting load balancers in between is kind of troublesome. We want to be able to scale out horizontally. We want to have automated response to failure. When something breaks, we shouldn't go any requests to it anymore. And we want to be able to be location transparent, to pick up a service, deploy it somewhere else, maybe another data center, and not have to change any infrastructure or routes in between. And we want to be able to do zero-touch, zero-downtime deployments. So currently we are doing zero-downtime deployments, but there's some manual work involved by deploying, for example, one service at a time. So what's our service discovery setup? We're using Console from HashiCorp, which is a service discovery service registry. And in this example, we have 2 instances of a service that's called service example. We have a console cluster running, and we have a web service where our frontend is running on, and an end user. So whenever the services start up, they register themselves to console. So now console knows for the service named service example, I have 2 instances, instance 0 and instance 1. Then there's a tool running on a web server which fetches data from console and then generates a configuration file for our frontend, which is basically a JSON file that has a list of endpoints, and for every endpoint a list of URLs. So it would contain something like service example colon service example 0 / service example 1, something like that, a bit simplified. So then whenever the user fetches the frontend from a web server, we set up we serve the Angular app, and then we set up a server sent events connection. So server sent events is a browser standard that's implemented by most modern browsers, except Internet Explorer, and it's similar to WebSockets. It's server push events. So we were able to do this because we only need to support Chrome and Firefox. If you're stuck with Internet Explorer, then it might not work. So what this SSE connection does is it's publishing updates to the browsers. So when the browser now does a request, it looks into service, wants to request a service example. It looks in its configuration file in memory. It says, all right, I can reach that service example 0 or 1. It picks one randomly and then does a request. And then the next request might go to service example 1. So let's say that an instance breaks, service example 0 breaks. Within a second or so, console will know because it's continuously calling the health check. Console template will generate a new configuration file saying that service example is now only reachable as service example 1. And then the SSE connection will push it over to the connected browser. So whenever we shut off a service or it breaks, within a couple of seconds, all connected browsers know that they shouldn't be sending requests to this service anymore. Whenever we scale out, we add services within a couple of seconds, all the connected browsers know that they can reach this service to send initial requests. So it's been working out fairly well for us. The patterns we're using here is client-side discovery, because the client, in this case the front end, discovers which clients are there. Whenever a service needs to call another service, we're using Spring Cloud Console and Ribbon, so it will automatically load balance over the dependent services. So it's a similar mechanism. We're using self-registration because whenever a service boots up, it will register itself in Console. And the added benefit is that we now have a complete overview of our landscape in Console. We know which services are running, which instances are there, what are their host names, and are they healthy or not. So it gives us a good overview of what we're running and which is healthy. And actually, when we moved to console and made all services register itself, we noticed some stuff we'd had forgotten or lost in the past that was still running but was not being used anymore. So, 10 minutes left. I might even make it in 40 minutes. How's the pace? Am I going too fast? Wave your hand. Going too slow? Wave your hand. Okay. So bear with me, the one person who thinks I'm going too slow. I'll do my best. So how do we develop stuff? We do feature branch-based development. So our master branch should always be releasable. And whenever we start building a new feature, we create a branch, we start building it there, and not until it's done, we merge it to the master branch. So we have our test environment running on OpenStack in our cloud, and this always runs for all services the latest version of the master branch. And feature branches only live on our local machines and on our CI environment. So it says 50 services here, but I think currently we're more close to 100, I think. So how do we run a system on our laptop that consists of 50 or 100 services? Do we check out 100 Git projects? I'd rather not. What we do is we only run the components that we work on locally. So if we want to work on one service, we only run this one service locally. And for all dependencies, we connect to the test environment in our cloud, which makes the setup on your local environment a lot easier. So testing-wise, I would say it's fairly standard. We do unit tests, mutation tests. How many of you have heard of mutation testing before? Okay, not too much. So mutation testing, you use a tool or framework that during a test deliberately makes changes in your production code without committing it to version control, obviously. But it deliberately makes changes in your production code. For example, instead of return true, it says return false. Instead of greater than, it says less than. And then the idea is that after every change, it runs your entire test suite. So the idea is that for every change you make, it should trigger at least one failing test. And if it doesn't, then this change isn't covered by tests. So your mutation test coverage says a bit more about the quality of your test than just your unit test coverage. Because if you're a bit proficient in Java, it's easy to write a piece of reflection code that touches 90% of your code without asserting anything. So the tool we're using is PyTest. There are also some JavaScript mutation testing frameworks. I would check it out. They're fairly good. So we do service and integration tests using Spring Boot integration. So during a build and during the Maven lifecycle, we spin up a Spring Boot container. So the application actually starts up and reads properties. And then for all the data stores, we use embedded in-memory data stores. In-memory MongoDB, in-memory Kafka, in-memory Elasticsearch. Then we inject data into these data stores, and then we use REST Assured, which is a testing tool you can use to call REST endpoints. So in an integration test, we're fairly close to testing the real thing that we will deploy it on our test environment later. Because Spring Boot container is running, it has checked the properties, it's connected to the data source, we have fetched data from the data source, and we have verified the correct return codes, response codes from our REST endpoints. So it doesn't happen too much that an integration test succeeds and then the application doesn't start up on the development environment afterwards. Whenever this happens, it's typically a configuration thing that we set a property wrong in the test environment property, something like that. For end-to-end tests, we use Protector, which is kind of the default for end-to-end testing Angular apps. And for load testing, we use Gatling. How many of you have heard of Gatling before? Okay, about 1/3. Gatling is a load testing tool based on Scala, Akka, and Netty. And you write your performance test in a DSL, which you're just writing code. So I think it's fairly good. So what we're doing is we're running a Gatling test suite twice a day, every morning and every evening, against the services on our test environment. We record the response times, and then response times are visible in this graph, which is deliberately unreadable, but it gives you an idea. So you see this line there. The line is the average response time of one service during the test. And the idea is that this should be fairly flat, because we know that the performance in production currently is all right. And if this line stays fairly flat during the sprint, then we won't see too many performance difference after we deploy it to production. If there's a peak, then probably we introduce some change that needs some investigation. So how do we test branches? Well, by spinning up the branch in our CI environment and test it there. Whenever we have dependencies, we connect to our test environment, and we avoid changing multiple components at once, because if you do change in 2 components, this mechanism doesn't work. In that case, we use the YOLO mechanism. We just push it, cross our fingers, and hope that we don't break too many stuff. So how do you build stuff and run it in production? We use GitLab, which is fairly good for on-premise Git. Jenkins with a couple of slave nodes provisioned by Docker Swarm. We use Jenkins 2 pipelines, which is awesome if you want to create reusable build definitions. Nexus and artifact store, and Sonar for quality control. I'd say it's a fairly default Java setup. So we have about 100 builds. How do we manage this with a single team or a couple of teams? By applying microservice principles to our builds. So we create reusable modular build definitions. Not going to go into detail, but I did a talk about this at the virtual Jug once. It's up on YouTube. You can check it out there. But pipeline as code in Jenkins 2 is awesome for creating reusable build definitions. So how do you deploy stuff? Every push to master of a service is a release. All the configuration for test, acceptance, and production is embedded in the executable jar. So the same binary travels to all environments. There are no secrets in the properties. These are provisioned differently. So we deploy stuff. Well, we used to do stuff with Rundeck and Puppet, which is okay. Currently, we're switching to Nomad, which is kind of a scheduler. Well, you could compare it a bit to Kubernetes. You can just say, all right, Nomad, here's a deployment configuration. Go deploy it somewhere. I don't have time to go in depth, but I'm happy to explain more about it after my session. So this is all per service. So for every service, a push is a release. So if you have 100 components, how do we know, and what's our administration in knowing when and what and which to deploy? Do we have huge Excel sheets or shoe boxes with notes in there? No, we try to not think about this too much and not to administer too much. So what we do is on a test environment, on every commit, successful build, we deploy. At the end of every sprint, we take, for all services, whichever versions are running on a test environment, take those and deploy those all together on the acceptance environment. After the sprint, we do the same. Take whatever is on acceptance, all those services version, and deploy this to production. But this also gives us the flexibility to deploy a single component from our laptop to test to acceptance to production. So it minimizes the amount of administration we need to do, while having flexibility of independently deploying independent components. So Graylog for logging is comparable to Elasticsearch Logstash Kibana, but a bit simpler, I would say. Metrics using Spring Boot Actuator. Zipkin for tracing requests over multiple services. Grafana for graphs, and then some monitoring tools using Sensu and Flapjack that, for example, monitor disk space or the health of services and stuff like that. So did we have challenges? Yes, obviously. Sharing, we ended up by sharing as little code as possible between services and try to prefer duplication over tight coupling of services. We had nice microservices backend and build a monolithic frontend. Try to think about modularity there too. I think there's a talk about micro frontends later today. We try not to be too afraid to throw away something we've built in the past, because if we built something 2 years ago, we open the code, we dust it off, we don't understand anything about it, then it might be faster to throw it away and build it again using our current standards than to try to understand and refactor the old code. We're running stateless, so we need to perform authentication and authorization at every request currently, because we're using Kerberos. So this has a cost. When we first went live for a considerable amount of users, we need to scale up our LDAP cluster like crazy to be able to handle the load, because we're calling LDAP for every request. So we ended up using a little caching there. There's always a balance between caching user details versus security. So we try to keep the cache period a bit short. It's vital to have teams that can do everything they need to do to go from idea to working software and production. So we need to have backend experience, frontend experience, testing experience, and operations experience in one team. And we have a very active product owner. There's lots of new ideas and throwing ideas at the teams like crazy. So what we used to do is put every new idea, start running and start building it. And in the end, we had 10 almost finished ideas. So what we're saying now is, all right, great idea, but wait, we need to finish this, get it in production first, and then start working on the new idea. So stuff we'd like to work on. Well, build cross-functional product teams. We've actually already did this. I have 2 seconds left, but we're going to work out. Final slide. We want to work on automated security testing. We're doing some stuff with OWASP dependency check, checking all our Maven dependencies if there are known security vulnerabilities in there. It's a great tool. But we don't have really a very good automated security test suite. So if you have any ideas about it, please approach me afterwards. I'll be happy to chat. We need to get better at dashboards and alerting. It's all right, but it could be better. We're still working on automated zero downtime deployments. So Nomad is really going to help there. The things we did with Console already helps. And we've actually already split up our front end in modular reusable components. So I'm currently 42 seconds over time. So there's no room for questions now. But feel free to approach me during the conference or reach out on Twitter. My slides are on Twitter. So I would say thanks for your time. Don't forget to vote at the entrance, and hope to see you around today. Enjoy your day.